Hello and welcome to a new video, in this case exercise number 4 of the Fourier Transform handout or lesson. In this case the exercise is shown here is telling that they have we have an LTI system. So we have an LTI system and there is a measure done on the system, and the following is done. So we input the complex exponential e2jwt, and basically what we do is we change the value of the frequency. We change this between a range that is over here. There is a typo. I put here absolute value of omega, which means that the sweep in the frequencies of the input exponential is the following. They sweep between omega 0 and 2 omega 0. So if 0 is here, omega 0 is here, 2 omega 0 is here. So the exponential takes value on all this range, and as it is an absolute value, then also we sweep on the reflected negative value. So between minus omega 0 and 2 omega 0, we also sweep this range. So sweeping this, we input exponentials, and what they tell us is that the output is the same exponential for this range. If the range is outside this range, so if we sweep here or here or here or here, then there is nothing at the output. So the system completely blocks any input exponential which is not within these intervals omega 0 to omega 0 or minus omega 0 and minus 2 omega 0. This is what is called a filter, because it filters the input frequencies, filters out, cancels the frequencies that are not within this interval, and it's called a passband filter. Passband filter, because there is a band pass, which in this case is these two intervals here. It's a band pass filter. You will see later on the class that we have other type of filters like low pass, high pass, and notch filters, but this is what we have. So a filter in short terms is just an LTI system with this behavior to the input frequencies or the input exponentials. So then they tell us that now the input to the filter, to this system, is not the exponential but the signal xt that we have down here, which is a periodic square wave. So, and they ask us what will be the output if the frequency of the input square wave is around a certain value in the frequency axis. Okay, so they tell us that if we call omega 1 to pi divided by t, which is the angular frequency of this square wave, then they ask us to calculate the output if the relationship between omega 0 and this frequency is the one shown here. So omega 0, it's between the period of the frequency divided by 2 and the period of the frequency. Okay, so what we need to do is to decompose x of t, decompose it in a summatory of exponentials. Okay, times whatever. Because if we are able to do that, as we know how the system behaves in front of the exponentials, we will know what will be the output. Okay, this sounds familiar. This is basically what we saw in the lesson of the Fourier series, which is that LTI system respond to the exponentials, the complex exponentials, in a way that they leave them pass or not depending on the frequency response of the system, okay? Which over here we have it here. The frequency response will be, we let them out, completely we let them out. So if we plot here h of omega, the frequency response, we just let them out completely between those intervals, and we just cancel, so it will be 0 outside this, okay? This will be h omega. So any exponential that goes into the system, we just know how to calculate the output, just multiplying by the value of h omega in this particular frequency. So again, what we need to do is to come up with xt and decompose it in complex exponentials, and then apply this h omega. So what we need to do, basically, to do this decomposition is we need to do the Fourier series of x of t, okay? We need to calculate the Fourier series of the signal x of t, because, as we know, the Fourier series will give us this complex decomposition in complex exponentials. Typically, in exercises before, what we did is go and calculate the Fourier series straight from the formula of the a sub k coefficients of the Fourier series, and you can do it, and I encourage you to do it. But for this exercise, we are going to take another route that we also saw in class, which is use the Fourier transform of x of t to calculate the coefficients a sub k, okay? This is not as straight a path as the taking the Fourier series, which they gave us straight the a sub k, but it's another way that in some cases like this is quite straight path to follow. Why? Because the way that we need to do that, remember, was take s of t, look at x of t, and isolate one single period of x of t. So if we take a look here at x of t, one single period of x of t could be this. For example, this 0, then goes over here to 1, then 1, and then goes down to 0 again, okay? This is a period of the signal. If you take this red part and repeat to the right and to the left, you will get eventually the full signal. So when the single period of the signal is a Fourier transform that we know, and this is the case because this is somehow a square or a pi function, then this path is also quite straight, and sometimes even more straight or straighter than doing the Fourier series. Why? Because if we take s of t, then we isolate a single period of x of t. Let's call it, for example, a single period of x of t. Let's call it rt. So rt will be this red signal that I am putting over here. And if you have rt, then you make the Fourier transform of rt, which is r omega. And once you have r omega, then the a sub k coefficients, remember, we're just taking r of omega and calculate that in the equally spaced frequency k omega 1, where omega 1 is 2 pi divided by t, divided by the period t. In this case will be t, okay? So in this case, this is quite straight. Why? Because the transformation of rt to capital R the omega is straightforward, because again r of t is a pi function and we know how to calculate. So that's another way of calculating this that we are doing in this exercise. So let's go ahead. So r of t, the red signal there, is, as we saw, it's a pi of t minus. So it's a pi that is displaced to the right this amount, and this is the period divided by 4. So it's time minus capital T divided by 4, and the total width of the pi is this, which is tau, capital T divided by 2. So this is R of t is this signal. Okay, so if we do the Fourier transform of that, it's also straightforward. We know it almost by heart. This is the total width, which is capital T divided by 2, sinc of capital T divided by 2, omega divided by 2 pi, and then we need to account for the time displacement, that we know it's an exponential of j omega and the displacement over here. Okay, so we have now R of omega, and then it's straightforward. Basically, once we have R of omega, A sub k is just taking R of omega and particularizing that for k omega 1 divided by t, capital T. Okay, A sub k will be taking this expression, this R, and substituting k for omega 1 divided by t. If you do that and make some simplifications, you end up with the following expression. You will end up with 1 divided by k times pi j square sinus square of k pi divided by 2. So please do it because it's an excellent exercise to calculate with exponentials and transforming them into circular series. Okay, so this is what we get, but as always remember that we need to check if the values of A sub k, they behave well with k equal to 0. So if we calculate with this formula A0, you can see that we have indetermination, because we will have 1 divided by 0 times pj in the denominator, and in the numerator we will have sin square 0 times p divided by 2, and this is a 0 divided by 0 indetermination. So this is very frequent that the general formula for A sub k does not fly for the k equal to 0, and in this case what we need is to calculate in separate the A0 term. So the A0 term, if we just calculate it with the formula of the A sub k, or if you just remember that this is the average value of the signal, which is 1 divided by t, so the duration in the denominator, and then the integral to a period of the signal x of t dt. This is A0 always. Okay, so in this case, this is the area of the signal, and if you calculate this is 1 divided by 2. So in this case, as happens in several cases, you need to calculate A0 in a separate calculation from the rest of the A sub k. Okay, so we are done. Let's summarize here. How do the A sub k terms look like? Let's summarize them over here, because we will use them from now on. So A sub k are, if k equals 0, then A sub k is 1.5, 1 divided by 2. If k is different from 0, we have two possibilities. Look, we have a sinus square of k p divided by 2. So we have a sinus square of an integer number of pi divided by 2. So if this integer number is odd, for example, k is equal to 1, then we will have the square sinus of pi divided by 2, which is 1. Okay, and so on and so forth. So basically it will just in this case be what is in front of the sinus square. So it will be 1 divided by k p j. But if k is even, look, then sinus square of an even number of times p divided by 2, for example, k equal to 2, so 2 times p divided by 2 is p, or pi, sorry, so sinus square is 0. So for k even, the coefficient is 0, A sub k. Okay, so we are almost there, if we, what we remember needed was to calculate the Fourier transform and see how does it look like in frequency. Okay, so up to now what we calculated is a sub k, but we know also that how to move from the Fourier transform to or from the a sub k coefficients to the Fourier transform. Remember that the Fourier transform of Fourier series, for example, x omega, it was 2 pi times summatory in k of the coefficients times delta of omega minus k times 2 pi divided by t. Okay, this we have, so we know how to draw this. Let's draw it. So it will be a train of deltas with different heights depending on the a sub k. Okay, over here we are going to write x of omega. Okay, the Fourier transform of the square periodical signal. So let's go step by step. For example, if we put k equal to 0, we'll have 2 pi times a sub 0, and a sub 0 is 1 divided by 2, times delta in omega minus k equal to 0, omega minus 0. So we will have a first delta function in 0 over here, with an amplitude which is 2 pi times 1 divided by 2, this is pi. Okay, so corresponding to the value k equal to 0, we have this first delta. Okay, let's take k equal to 1. So k equal to 1 will give us another delta, let's write it over here, which is in k times 2 pi divided by 2, as k is equal to 1, it will be a delta in 2 pi divided by capital T. And what is the height of the delta? It's 2 pi times a sub k. As k is 1, is odd, we can use over here the formula. It will be 2 pi times 1 divided by 2 pi j. Okay? And but divided by pi j, and this is 2 divided by j. Okay, and again this corresponds to the value of k equal to 1. Okay, let's put also k equal to minus 1. Okay, so k equal to minus 1 will give us another delta in minus 2 pi divided by 2, which is 2 pi divided by capital T, And the amplitude, it will be the same, but with a minus sign here, minus 2 divided by j. If we go, for example, this, let me write here, this will be the corresponding term to k equal to minus 1. Let's do one more term, just to have a feeling of how this goes forward. So the next one will be k equal to 2, so it will be 4 pi divided by t, 4 pi divided by capital T, and the amplitude will be 2 pi times 1 divided by 2 pi j, and this is 1 divided by j. This is the term corresponding to k equal to 2. On the left, we have seen we will have exactly the same, but the amplitude will be the same, but negative. So we will have another delta in minus 4 pi divided by t, and the amplitude will be minus 1 divided by j. Okay? So here I am kind of writing in a loose way, because I put this is x of omega, and you can see that the amplitudes are not integer numbers, but they are complex numbers. So in a strict fashion, we should draw two diagrams here for the magnitude and for the phase, but typically when the amplitudes are imaginary numbers, this can be drawn and is quite self-explanatory and useful to do so. Okay, so and then we could keep here to the left and to the right, repeating these deltas. This is the spectrum or the spectra of the periodic square wave. So now they tell us that we pass this through our LTI system. And remember that our LTI system had this frequency response. Okay, so anything between omega 0 and 2 omega 0, it passes, and outside these values, also in the negative side, they are cancelled. Okay, and they tell us that omega 0, this omega 0 is between omega 1 and the half omega 1. And omega 1, it was, remember, 2 pi divided by t. So omega 1 is this one, okay, and this will be 2 omega 1 divided by 2 omega 1, sorry. So they tell us that this omega 0 is somewhere between half omega 1 divided by 2, that will be, I don't know, over here, for example, this will be omega 1 divided by 2, and omega 0 also all the way up to omega 1. So what we will have is a filter that could start from here up to here. This will be the minimum part, and the maximum will be this one, also in the left. Okay, and typically, for example, we will have a filter, for example, that is over here. Okay, amplitude 1. Okay, and the same to the left. So what we are seeing is that if omega 0 of the filter is within this range, how this filter will actuate on this x omega, we can see it will only let pass the delta that is corresponding to k equal to 1. So this delta will pass, and all of the rest of the deltas, so the delta that is at 0, the delta that is here, and also on the left, the delta that is here, and so on, will be rejected. The only that will pass will be this delta and this delta. Okay, and again, because the filter has the windows right into these deltas over here. Okay, so we are almost done. If we multiply then x of omega times the response of the filter, basically what we will have is these two deltas. We will have a delta in 2 divided by j and center into 2 pi divided by t, and we will have another delta in amplitude minus 2 divided by g and center into 2 pi minus 2 pi divided by t. Okay, this will be what we will have here. This is x, this is capital H, and this is x times capital H. How do we calculate the inverse Fourier transform? We call that the output y of t. So y of t is the Fourier transform, inverse Fourier transform of that. And this is very easy because look at this. If you put a 2 on the front and if you divide by pi, what you have is pi divided by j, and the delta on the right minus the delta on the left. And this, remember, is a sinus. The inverse Fourier transform is a sinus of 2 pi divided by t, capital TT. Okay, so that's easy. The final Fourier transform will be inverse Fourier transform. The signaling time will be 2 divided by pi, the sinus of 2 pi divided by t, capital T, t. This will be the output of the signal. Okay, so I hope it's clear. Nice exercise. I encourage you to work hard on this exercise to really understand it. Brief summary: we have a filter which filters out, is a passband filter, and the passband is the one between omega 0 and 2 omega 0 to the positive and negative frequencies, and then we input this signal periodic square xt. What we do is we calculate the Fourier transform of x of t, and to do that we calculate first the Fourier series of x of t. The way that we calculate the Fourier series is on the way of applying this formula over here. We calculate the Fourier transform of the elemental period, and once we have the Fourier transform, we calculate the Fourier series, or the coefficients of the Fourier series. If we have the coefficients of the Fourier series, it's straightforward applying this formula here to calculate the Fourier transform. And once we have the Fourier transform, which is written over here, down here, applying the filter is only selecting which are the deltas that pass and which are the deltas that they are blocked. In our case, 2 deltas are passing and the rest is blocked. So this is the result and the inverse Fourier transform. So hope this is clear. I hope you enjoyed, and see you in the next video. Bye-bye.